at the very top, the orange button.
Oh.
Hello, everyone. Welcome to the UFS Webinar Series. I hope you're doing well this afternoon. Today's webinar series is going to be about improving weather forecast skill and rainfall climatology of FV3GFS using machine learning by Chris Bretherton. This is Bhavana from Office of Science and Technology from the National Weather Service. We are hosting the webinar, and I'd like to hand over the introduction of the speaker to Lucas to introduce Dr. Chris Bretherton. Thank you.
Thank you so much. So it's a great honor today to be able to introduce Professor Chris Bretherton of the Departments of Atmospheric Sciences and Applied Mathematics at the University of Washington, my own alma mater. And also he's a Senior Director of Vulcan Climate Modeling. Vulcan Climate Modeling at which is a really great opportunity that we've had to be able to collaborate between the two institutions. Chris is probably one of the nation's foremost academic modelers. It's a great honor to be able to work with him. He is in particular an expert at cloud formation and turbulence within climate models. He's applied a very vast array of different techniques to be able to better understand and processes within weather and climate models over his 3.5 decades of research now. He's been at UW since 1985, and then since 2019, he's been the Senior Director of climate modeling at Vulcan, and has been collaborating with GFDL to use machine learning to improve prediction of precipitation, weather, and climate models. Chris has won many awards, including the AMS Charney Award, has been the AMS Harwitz Lecturer, is a double fellow both AMS and AGU, and has been an IPCC lead author, and is a member of the National Academy of Sciences. And so I don't mean to drag this out long enough, but yeah, as I mentioned, it's been a great honor to work with him. And yeah, so I'm hoping that we can continue to accomplish some really neat stuff. He's got some great, him and his team made some great progress so far, and we're really excited where we can go in the near future. So anyway, thank you, Chris. Take it away.
Hey, thanks very much, Lucas. I'll try and show my screen right now. I'm not sure what, okay, let's see. What can you see right now? Can you see my first slide, or are you still seeing my face?
We see the slide.
Okay, great. Okay, so we're good. So I'd like to talk to you about an exciting collaborative project between GFDL, where Lucas is, and Vulcan, which I'll describe a little bit more in a couple of slides, to try and use machine learning to improve aspects of the FV3GFS. Mainly, we're thinking of FV3GFS actually here as a prototype climate model, but I think weather and climate are really two sides of the same coin here, and the developments here will also be, I think, very much relevant for weather forecasting as well. So I'm speaking on behalf of a small group given at the bottom of the slide working in Vulcan Climate Modeling, as well as Lucas, who's our GFDL collaborator. Okay, Vulcan Climate Modeling is a philanthropic open source project of Vulcan incorporated in Seattle. So Vulcan was founded by Paul Allen to manage his assets and philanthropic interests. And continues that way after he passed away a couple of years ago. And in particular, Paul was, at the end of his life, very interested actually in climate change, and especially in trying to improve climate modeling using modern software and hardware. So the result of that was this project, in which two interlocking groups was spun up in the middle of 2019, partnering with GFDL. And basically, the reason that we partnered with GFDL was that they had a very high resolution, 3-kilometer global version of the FV3GFS which we could use as a reference data set for our machine learning. The goal of my co-director, Ollie Thuro's side of the project is to use what's called a domain-specific language to rewrite FV3GFS to run faster on modern GPU-enabled supercomputers. Right now, at least at GFDL, FV3GFS is run on a CPU-based machine, Gaia, but the future of high-performance computing is accelerator architectures of various kinds, and so we'd like to make sure that that's an easy transition and can also flexibly adapt to new generations of accelerator technology to enable multi-year climate simulations with 1 to 3 kilometer global grids. My part of this then is to take what we hope are the hyper-realistic simulations that those produce and use machine learning to train parameterizations of coarser grid climate models that are more affordable, 25 to 200 kilometer grid models, to take advantage of what we hope is the better fidelity of these very high resolution models. And our unique niche in this problem is that we are directly trying to go for a full complexity global atmospheric model written in decades of Fortran. So dealing with this problem, not in an idealized setting, but in a real setting where the research to operations transition could be quicker. Our group at Vulcan Climate Modeling consists of 2 teams, as I mentioned, and my team shown on the left, Ollie's team shown on the right. And I think of note here are that both teams have members embedded at GFDL, Spencer Clark on my team in particular. Ollie's team actually has a collaboration with ETH in Zurich in Switzerland and has a member there too. So, and we also have a collaboration with NASA on that side of the house. So we're broadly distributed. The inspiration for this project was NOAA's global model, FV3GFS, run in its modified version, XShield, at GFDL. So this is an example of XShield cloud distribution. Just to show you why this is inspirational for us, you can see lots of multi-scale cloud features. It's explicitly resolving convective storms and things like the clouds associated with cold air outbreaks. And of course, can handle the details of topography much better than a 25 or 200 kilometer model. This model certainly seems like it has the potential to be a very good reference model for machine learning for a coarser resolution climate model. Now, just to show quantitative evidence about the utility of high resolution models, this compares a 40-day, 3-kilometer global simulation using XShield as part of the Diamond intercomparison. So this is August to September of 2016. It's a free-running simulation initialized from reanalysis. And so what's shown is the 40-day climatology of precipitation in the 3-kilometer model. In particular, what's shown is the bias compared to GPCP. And what's shown on the right is exactly the same thing run with a 200-kilometer version of FV3GFS. And we're just focusing on precipitation biases over land because that's Vulcan's interest. That's where people live. That's where the impacts of precipitation are really felt. And what you can see is that there are certain regions of the globe where the 3-kilometer model really does a better job. And so I'd call attention to the Himalayas in particular during the Southeast Asian monsoon, and also sub-Saharan Africa, where the GFS is showing a strong negative precipitation bias, but XShield is not. So really the question here is, can we use machine learning trained on the 3-kilometer simulation to improve especially the rainfall distribution in this coarser FV3GFS simulations? So in order to understand our approach, let's go down to equations. So here we'll focus on heat, moisture, and horizontal momentum equations, which have advective sources in them, the v dot grad terms, and then they have the so-called apparent heating, moistening, and momentum sources, Q1, Q2, and QU and V. So in a normal numerical weather prediction model, these would be handled by the physical parameterization suite. They would consist of radiation, boundary layers, surface interactions, cloud microphysics, etc. Now, we can then use machine learning to replace the Q1, Q2, and QU and QV, or we can replace some of those parameterizations, or we can just add a correction on the Q1, Q2, and QU and V. Our approach in this project is going to be to leave the advective part of the solver alone. So we're not going to try and machine learn the advection. We're going to try and machine learn these heat, moisture, and momentum sources. And in particular, we're going to take the same approximation that's typically used in conventional parameterization of assuming that these things can be represented in terms of the column physics, the column temperature, moisture, and wind profiles, as well as the surface properties, sunlight, etc. And the outputs will then be tendencies of humidity, temperature, and winds, as well as relevant diagnostic quantities in that column. The simplification is most appropriate when the grid boxes of your model are much wider than they are high, which is true for the target horizontal resolutions that we have for this. So let's now go and talk about what we use for machine learning. So I mentioned a 3-kilometer model for machine learning, but that's not the only possibility. Our goal in general is to train a column-wise machine learning correction, could also be a replacement, but here I'll show a correction, to supplement the physical parameterizations of a coarse grid climate model so it evolves like a more accurate reference data set. That reference data set could, in fact, be a reanalysis, which has the advantage of being data-driven. This is actually quite attractive for climate, but it is limited to recent weather variability in the satellite era for training. And it would be ideal for this purpose for the coarse model to actually be the same model that assimilated the data for the reanalysis, which is not the case in, not exactly the case in our simulation. The other possibility is to use a fine grid global model. In this case, what we do is we coarse grain the fine grid data to the coarse grid using horizontal block averaging. So this allows us to use these 3-kilometer global simulations that GFDL is doing. Of course, they are short, but we can conduct them over a range of idealized climates, for instance, by changing the sea surface temperature assumed in the model. And previous work suggests this can work quite well in idealized settings, such as a water-covered Earth. But on the other hand, it's only as good as the fine grid simulations, which in general will still have biases. Now, I should also stress that our machine learning has some interesting twists. It's a hybrid application of machine learning in which we're coupling our machine learning to the fluid dynamical solver of the weather model. So in training the machine learning, we basically are keeping the fluid dynamics fixed. We're assuming we know that. But in testing it, we have to not only test it offline, as we do as part of the training process, but we have to test it, more importantly, online in actual forecast modes. And so in addition to offline skill, our machine learning has to produce stable simulations. That's not guaranteed. Given that it's stable, we would like it to produce accurate weather forecasts, and we would like them to have low climate bias. So these 3 components of online machine learning skill, we can only evaluate running our machine learning in forecast mode after we've already developed it. I'd also like to talk for a second about our workflow, which is kind of an interesting example of both the pros and cons of our collaboration with GFDL. So Gaia is NOAA HPC. It sits behind a firewall, which basically makes it inaccessible to our team at Vulcan. In addition, we are trying deliberately to work with a community version of FV3GFS, while the X-Shield model is customized by GFDL. This introduces some interesting wrinkles. Lastly, Fortran is not exactly the language of choice for machine learning. And at Vulcan, we have no compute infrastructure. So we had to deal with these software challenges. And so in order to deal with them, we actually adapted FV3GFS to Google Cloud. We custom created a Python wrapper that goes around the components of FV3GFS to allow us to access them and modify them using machine learning. And to keep the data sets small enough, we actually added inline coarsening into the shield model so that we only have to output the output of the 3-kilometer simulation at the coarsened resolution that we want. And we pipe this into our machine learning workflow on Google Cloud Platform. So there's actually a lot of sophisticated software engineering that we had to do to make all of this work. That would actually be it would be interesting for other groups to try to adapt. I know that there are other groups that have run FV3GFS on the cloud, but our approach is open source, and so we would definitely welcome sharing it with other groups. Now, the machine learning we do is based, or was originally going to be based on something called the tendency difference method, or what I call a tendency difference method. So the idea of the tendency difference method is that you have a reference model whose time evolution you know as a function of time and position, and a course model denoted by a star here, which initially has no machine learning in it and has an advective term and a physical parameterization term. So that physical parameterization term is this QAP in this top equation. So then what we can do is we can identically initialize the course model and to the coarsened version of the fine resolution of the reference model, be it a reanalysis or a coarse and fine model. And then we can calculate the initial tendency of the coarse model, and we can compare that to the tendency of the fine model of each prognostic variable at each position in time. That tendency difference, delta QA, we would like then to machine learn as a function of the atmospheric column state. And ideally then, if we were to perfectly learn this and add it to the coarse model, that would cause the coarse model to evolve in lockstep with the fine resolution model. Now, of course, we can't exactly learn the delta QA, and so there will be errors in that process. And in fact, there are a variety of complexities here, which I'll describe. This method was in fact developed earlier, and we used it at the University of Washington for aquaplanet tropical channel simulations using a 4-kilometer fine resolution reference model and a 160-kilometer coarse model with some moderate success, I would say. Here, the new part is using it for a real geography planet and a real full complexity Fortran model. Some things we did differently, it turns out we used random forest machine learning rather than neural nets initially for stability. And the big complication here turns out to be topography. So the lower picture on the right shows a cross-section across the north slope of the Himalayas, and the white indicates the topography in the 3-kilometer model, and the red vertical bars are indicating the coarse resolution grid cell edges. So we have to represent the topography in the coarse model basically by one value over that entire coarse cell. Actually, it's more like a slope, but in any case, there's clearly a lot that we are not resolving here. And so when you, for instance, if you try and coarsen or in any way interpolate the 3 kilometer output to a much coarser resolution, you'll lose something. And in particular, it ends up causing initialization transients in the coarse resolution model. And these ended up being crippling to us, in fact, such that we had to abandon this. And just to show you why, it won't be a surprise to anyone who has tried to initialize any kind of an NWP model. What we find is if we initialize with the coarsened, well, actually, in this case, a coarsened fine resolution model, coarsened to 200 kilometer resolution, whose vertical velocity at 500 hectopascals in particular, at one particular time is shown on the left panel, then after 7 minutes and after 14 minutes, vertical velocity transients very rapidly develop in the forecast. So actually, this is an average of 348 initial conditions. What you can see is a bunch of speckle showing up over the Himalayas in that red boxed region and in other mountain regions, which basically indicate large vertical velocity transients that develop. And basically these screw up our machine learning. They make our training data set close to unusable. So we had to do something different, and what we came up with is a nudging tendency method, which also works nicely with reanalysis as the reference data. So in this case, what we do is rather than make the coarse model track exactly like the reference model, we nudge the coarse model to the reference model. That's that middle equation. And so the nudged coarse model has prognostic variables AN at each position in time. And then we learn the nudging tendency, which basically is the tendency that's required to keep the coarse model behaving reasonably close to like the reference model. And in this case, again, we're learning it as a function of the coarse model state. Now everything is in the choice of nudging timescale, and on sort of theoretical grounds, we chose to use a timescale of a few hours. You have to make it long enough, or else you end up with a version of this initialization transient problem, but you want it to be short enough to keep the coarse model close in state to the fine resolution reference model. So, okay, so first, let me show you some results where, as our reference model, we use an NSEP observational analysis. It's available 6 hourly, so we used a nudging time scale of 6 hours. We trained on a full year of analysis data, and we learned the nudging tendencies of the velocity components, temperature and humidity as a function of column state. We had to include a limiter on the moisture in prognostic runs to prevent the machine learning correction from creating negative humidity in forecasts. And if we do that, then our performance using random forest machine learning was quite encouraging. And I'll show you these results shortly. But in particular, we were able to improve the weather skill of the 200 kilometer model without machine learning, reduce its rainfall bias. This machine learning corrected model runs skillfully over an independent validation period, which is where I'll show you the results from, with different sea surface temperatures. And other climate biases were mostly comparable to this baseline version of FV3GFS. We are starting to be able to use neural net-based machine learning to achieve comparable forecast performance, but this actually has required considerably more effort in basically configuring the neural net. Just to talk about how we do machine learning for this, what we do for this 1 year training data set is we sample the nudging tendencies every 5 hours. We want to sample irregularly around the diurnal cycle, so we don't use something like 3 or 6 hours here. And we subset the nudging tendency data sets to 160 times, where each of which we have global a global data set of 13,000 coarse grid columns. So this gives us 2.2 million training samples, 2.2 million columns, and then we use that for the machine learning and test it on an independent sample of 90 times, or 1.2 million samples. And so our input features, in addition to the column profiles of temperature, humidity, and winds, are insolation, land sea mass, and the surface geopotential. So now let's just show how this works. So in the mean, random forests are actually very good. Now I should say, of course, we're trying to predict all of our nudging profiles at each position at each time, and they're all so different at all times. So I'm going to show you this data boiled down to column integrals of the nudging tendency of humidity. So this nudging tendency is in the form of a moistening. So this is a column integrated moistening tendency and averaged over the entire test sample of times. So what you can see here on the left is a map of this. So it has some geographic structure, and it's mostly blue. And what this indicates is that the coarse model, when faced with the reanalysis temperature, moisture, and wind profiles, doesn't like to rain enough. It basically doesn't like to convect enough in the tropics. And so as a result, it gets too moist. And so then the nudging tendency, nudging it back to the reanalysis, says, oh, you got to dry this out. And then basically that means that the nudging tendency is pretty significant. There's over 1 millimeter per day of global mean drying that has to be applied to keep the baseline model balanced in sync with the reanalysis. And the machine learning scheme is able to learn this quite well on average over the period, and gets the right geographic distribution. It naturally smooths basically noise in the target data set, which is good. And it has the same vertical profile shown in the upper right in global average. Now at individual locations and times, the agreement is much noisier. And now I wanted to show you how this works in tandem with the physics. So on the right are the column integral of the heating and moistening tendencies from the physics. So these, for instance, show the obvious effect of the diurnal cycle as the sun goes around the globe, heats the surface, creates a bunch of heating of the atmosphere as the surface fluxes rise up into the atmosphere. They can create a bunch of precipitation, which is kind of the flashing blue dots there, which can locally dry the atmosphere. In other regions over the oceans, there's a lot of evaporation, which is going into the ocean. Those are those red regions, which is not balanced by local precipitation. So then the machine learning corrections is shown in the middle, and they're on the same scale. And you can see that they're actually of comparable magnitude. But you can also see they're not varying nearly as much. They are varying from time to time. There's flicker in these fields, but they're much more constant. So these corrections then basically act in tandem with the figures to give it with the physics to give the overall heating and moistening shown on the right. So these corrective tendencies basically are preventing drift of the baseline model to its biased internal climatology. Okay, so does this help? Well, actually it does. So here, what I'm showing you is RMS error growth in 12 forecasts initialized in the first day of our independent validation year, 2016. So the black curves are RMSEs of the baseline model as a function of forecast lead, going from 0 to 10 days. And the blue, the blue is if you only machine learn the temperature and moisture nudging tendencies, and the red is if, in addition, you also machine learn the momentum nudging tendencies. So you can see that for 500 millibar height and surface pressure, you gain a lot by actually nudging the momentum and learning the momentum nudging. for the lowest layer temperature, you get most of the benefit out of nudging the temperature and humidity. So it's much more affected by the that aspect of the physics. But overall, the red is almost always to the right of the black, indicating you're getting increased forecast skill. And for sea level, for surface pressure, you gain about a day and a half of skill at 4.5 days of forecast lead. So the skill is pretty significantly increased. You also gain in precipitation errors. So if you consider the annual mean precipitation errors, a year-long free run of the baseline model for 2016, compared to GPCP, you get the plot in the upper right. You see errors that are anywhere from -10 to 10 millimeters per day. And in particular, the very large errors over the Himalayas, especially over Central Africa and over the southern part of the southern part of the worm pool north of Australia. If you look at the ML corrected simulation in the lower left, you can see that those errors have been significantly reduced, and the overall pattern RMSE has gone down by about 20%. In fact, almost 25%. If you only correct the temperature and moisture, you get, in fact, already a large fraction of that improvement. Now, not everything is as good as this. So we can look at global mean precipitable water. So here, our reanalysis is the light blue line, second from the top. What's shown again is the analysis precipitable water over the year of 2016. So it has a annual cycle. The dark blue is the baseline uncorrected run. So it drifts moist and then basically has the same kind of annual cycle. And the green is the machine learning model. So it drifts a little dry, but then is able to basically track along with the reanalysis just fine for the rest of the year. So in this case, the bias is comparable to the baseline, and it's on the order of, I think, 2 millimeters or so, which is acceptable, not great. But if you look at the temperature biases, so this is now a zonal average plot. So zonal mean temperature versus pressure. So I think pressure going from 1,000 to 0 on top. You can see some pretty bad biases compared to the baseline. So the baseline run has biases up to maybe 5, so at most, well, less than 10K at all heights and latitudes. The machine learning run has places like in the polar lower stratosphere where the bias is up to 30 degrees K, and even the surface biases in the polar region and temperature are pretty substantial. So that's the worst. I wanted to say this also works for precipitation at higher resolution. So we've tried it at C96, which is 100-kilometer resolution. And once again, if you compare the precipitation RMSE at the baseline run, which is now slightly reduced to 2.92, this is again the RMSE at the annual mean precipitation, with the ML corrected run, which is in the lower right. The ML corrected run is actually making about a 25% improvement. Currently, we're trying to test the same thing out at C384, but that's work in progress. Okay, well, now I wanted to continue to talk about nudge-to-fine corrective machine learning, where we use as our reference model a fine grid simulation. So first, I'll show you results where that fine grid simulation is the 3-kilometer X-shield version of FV3GFS, for which we only have a 40-day reference run. So I'll only be able to show you 40-day simulations there, trained on 40 days of data. But we also then did this with 25-kilometer version of shield, where we could run it out in multiple climates for a year. In this case, our nudging timescale was 3 hours. And again, there was a trade-off involved in this. And again, now we're learning, machine learning, the nudging tendency Now then it's the nudging tendency of a coarsened version of the fine resolution model. So the fine resolution output coarsened to the coarse resolution by horizontal pressure averaging as a function of the coarse model column state. And let's just show some results. So in this case where we're nudging to the 3-kilometer model, we're only working with the, well, at least in the results I'll show you, actually the results I'll show you show results where we both nudge just the temperature and moisture, and we also nudge temperature, moisture, and winds. And if we look at the column integrated moistening and heating, so in this case, moistening is on the top and heating is on the bottom, and blue indicates drying, we can see exactly the same thing we saw with nudging to reanalysis, which is that the target of the reanalysis is that we typically have to do drying with the nudging correction, quite a bit of drying. Again, the time mean over the 40 days is shown on the left of the amount of column integrated drying that we have to do. And both the random forest with or without the wind nudging sort of capture this pattern pretty well with some smoothing. We use a neural net to do the same machine learning. We get a much stronger pattern, which in some ways better matches the target, but sort of overshoots it in places. Same with the heating tendencies. So this shows that the neural net and random forest are trying to do the same thing, but the random forest tends to damp some of the variability while the neural net tends to follow it a lot more. Again, if you look at vertical profiles of, say, the machine learning, heating, and moistening, all of our methods are actually able to capture the time global mean profiles of the heating and moistening from this target nudging tendency just fine. And again, I point out to you, these are large amounts of drying and heating that are done. We're talking about machine learning having to do basically 1 millimeter per day in global average of time mean drying, which then has to go as precipitation into the land surface from the machine learning scheme. Okay, so let's see how this works. Regardless of whether you use machine learning, random forest, or neural net machine learning, we're able to increase the coarse model forecast skill in 10-day weather forecasts and improve the mean rainfall distribution over the 35-day average. And you may ask, is that long enough to make a useful comparison? And the answer is, I believe, yes, it is. This is a fairly robust result. However, there are still some undesirable mean state biases, which I'll mention too. So just to demonstrate the forecast skill, so here the baseline physics on is the gray, dark gray curve, which may be a little bit hard to see. And now I'm just showing 500 millibar height and surface pressure as metrics. And the orange curve is our best random forest, so with the wind nudging included. And you can see that in general, again, the orange curve is to the right of the, and below the dark gray curve, indicating it has better forecast skill. At some leads, quite a bit extra better forecast skill. The neural net is also able to do some of this. It's only using temperature and moisture nudging. And the random forest with just temperature and moisture nudging also has some improvement. But for these two metrics, not nearly as much improvement. There's a huge improvement from the wind nudging, which we think is due to there being excess drag in the model, excess orographic drag probably in the 200-kilometer FV3GFS. We also improved the precipitation just as for nudge-to-obs. In this case, the improvement is actually fairly comparable. The baseline physics RMSE of this 35-day period is 3.5 millimeters. And the pattern error of the 35-day mean rainfall, first 5 days we've discarded, but a spin up is now as little as 2.78 millimeters per day, or again, about a 20% improvement. Slightly less with the neural net. We also improved the diurnal cycle of precipitation over land relative to the baseline, which was of interest to us because this is a hard problem for coarse resolution climate models. So in this case, the dark gray line, which is kind of hard to see, is the diurnal cycle of the baseline model. It's not very pronounced. The light blue line is the fine resolution target, which has a later diurnal cycle and also much stronger. And say the orange model is the random forest with winds, which shows a larger diurnal cycle that's a little bit closer than the original model to having the target diurnal phasing. So it's bigger and a little bit better. It's not there, but encouraging progress toward it. So lastly, I wanted to show you something about climate change prediction to show you this can actually work in a climate context too. So for this purpose, I'll show you 40-day simulations now with a 25-kilometer model with control SSTs, SSTs increased by 4 degrees and SSTs decreased by 45 degrees. So we make these runs on Gaia rather than the cloud. And so the goal here is to see, could we train one corrective scheme based on the fine resolution 25-kilometer model across a range of climates to achieve a consistent improvement to the coarse resolution climate and climate change response. In other words, make them closer to what the fine resolution model is doing. So again, the results are that in all 3 climates, we can beat the baseline 200-kilometer model in matching the forecast from the fine resolution model on short time scales. And we're also able to beat its rainfall predictions, time mean for rainfall predictions over this period, including the difference between the control and warm climate. And we've tried to do this with 1-year training runs, like we did with nudge-to-obs. And here we're still having some problems, which hopefully we'll solve in the near future. Just to show you one picture here, let me just show you then the fine resolution difference between precipitation in a control climate and one with SSTs warmed by 4 degrees. So sort of a nominal warmer climate that we can produce in this uncoupled model. And so what we'd like to do is we'd like to match the differences in the fine resolution model in terms of the precipitation. Those are the precipitation trends, if you want, as the climate warms. And so the baseline model predictions of those precipitation differences, 4K minus control SSTs, as shown in the second plot from the left. And they have an RMSE difference from the fine res of 3.6 millimeters per day. With our all climate trained machine learning, we're able to reduce that pattern error to 3.2 millimeters per day right now. So not all the way to what the fine res model is doing, but certainly a little improvement. And we think we can improve quite a bit further on that. Lastly, I'd just like to mention emulation. We've also worked on emulation of FV3GFS physical parameterizations using machine learning. We've successfully emulated the PBL scheme and the deep convection scheme, but we found this a more difficult problem than we expected. It wasn't just to turn the crank for us. We're continuing to explore this, inspired by more successful results by Alexei Belachitsky and Vladimir Krasnopolsky at AMC, who've shown what we consider to be pretty impressive results. So we're hoping to see if we might be able to duplicate them. And if we can't, we're going to be knocking on their doors virtually to see what we can be doing better. So in conclusion then, we, in partnership with GFDL, have developed a sophisticated cloud-based workflow for applying Python-based machine learning to FV3GFS. Our corrective machine learning schemes improve the skill of global weather forecasts and the time mean rainfall distribution compared to 2 kinds of reference data sets, reanalyses or fine resolution simulations. And basically, this is a way to help an affordable coarse grid climate or weather prediction model capture precipitation trends in an expensive fine grid version of the model. Our current short-term goals are we have issues with our land surface coupling. And if we couple to the ocean, we have surface flux biases that would impact coupling to that too. I think we know how to deal with those. They have to do with cloud biases in both the original FV3GFS and even worse in our machine learned version of it, which has less precipitation from the physics parameterizations and hence way too little cloud. We've got to systematically reduce some other climate biases like that polar temperature bias I showed you. We think we have some handle on that. Demonstrate our machine learning methods, ideally, for instance, for even C768, the operational GFS resolution, and progress further with neural net learning. And for our nudge-to-observations method, we actually have recently submitted a publication to GRL, whose preprint you can get at the link below. We also have submitted something on our Python wrapper, which I think is also a really cool way of making FV3GFS accessible to a broader community for a broader range of applications, which is also a public domain piece of software. So thanks. So I don't know how we're going to deal with questions then.
I think if you would like to read the questions and answer them.
Okay, I'll have to look in the chat then. Let me see if I look at the chat. Okay, so hopefully someone has some questions. Maybe questions or chat. Okay, wait a second, I see questions now. Okay, fine. So I have a question from Ricky Rude. Sorry, glasses required for this. Are there qualitative morphological changes in the representation of mesoscale convective systems in the MJO and the 3-kilometer simulations? For sure, the 3-kilometer simulations can represent mesoscale convective systems. And of course, the 200-kilometer or even the 100-kilometer version of FV3GFS can. So sure. Now our training data set here and the diamond runs that have been done at GFDL so far have only been 40 days. So what Lucas knows about those is that he does get a better representation of tropical convectively coupled waves, but it's kind of short to look at the MJO. We're hoping to do year-long simulations with that same model that will start to get at that question.
So Chris, I just want to follow up on that. Is that, yeah, so I mean, like the sort of models we're developing at GFDL, both the FV3GFS and the climate models, they have pretty good representations of the MJO at 100-kilometer resolution and 25-kilometer resolution. And we find with our variable resolution approaches down to 4 kilometers that we can get a very nice MJO indeed that matches predictions very well at 40 days. So that's certainly yeah, a point to something we do want to point out. But yeah, it is true that going to increasingly high resolution does give you better and better MJO forecasts, even if you don't necessarily need 3 kilometers to get a good MJO.
So an interesting, yeah, and an interesting version of an interesting fact about X-Shield from that point of view is that at least by default, it doesn't run with specified sea surface temperature, but it actually runs with a nudged slab ocean. So where the SSTs are nudged to reanalysis on, I think, an adjustable timescale, which is, I think, typically 5 days. But that allows the SSTs to respond a little bit to the MJO2, which is considered by many climate modelers to be important for getting a more realistic MJO for sort of longer timescales. Okay, let's see. I have Brian next. I showed a map of ML nudging tendency of temperature and humidity. They're smooth and don't change much in time. Well, they actually change more than it looked in that plot. They do blink a lot, but they change on very small scales. How much of the skill could be got from a simple climatology of the nudging tendencies? Well, actually, we tried that. And the answer is making the nudging tendencies state dependent is important. we actually tried learning tendencies using monthly climatology and then applying them to this. And we were not able to get an improvement in the model climatology systematically that we are here, say in rainfall climatology. So yeah, I think that the method actually does matter a little bit, even though I agree, it looks like most of the improvement is happening from long time scale, large space scale errors. That would be an interesting thing to look at a lot more. Now we have this methodology down a bit better. Hopefully that's good for you, Brian. Let's see, Cliff Mass asks, do you have a comparison of forecast skill of a convection allowing model compared to the ML assisted course model verified over some region? Well, we have not looked at individual regions, and here we have not looked at the skill of the convection allowing model. In fact, the version of the convection allowing model we were looking at here was actually nudged in temperature and winds on a 24-hour time scale itself to ERA5. And so, so that would be an unfair comparison with this version. With the original Diamond version and with the Diamond 2 simulations that are now being done with FV3GFS, we could do that and we will do that. And I expect we have a long way to go to achieve the forecast skill of the original Diamond simulations with our coarser resolution ML version, but that remains to be seen. Okay, let's see. How sensitive would the results be if the training precipitation data set is changed from GPCP to something else? Well, that's a good question. And we haven't looked at that too much. Now, the context in which we have looked at this was actually in looking at the diurnal cycle, which we don't have actually for GPCP, but for which there are a couple of data sets out there. And let's see, I'm trying to remember the names of the data sets at this point. Maybe Lucas can remind me. There was one called I can't remember, but let's just say there are big differences between those data sets. And there's, in particular, one big difference is actually in what the global mean precipitation is. And that's, that's of importance here. But in particular, they had big differences in the mean precipitation over land. So yeah, the answer is they'd be a little bit different, but the biases we're talking about are several millimeters per day in time mean. So I suspect they would not be vastly sensitive to that. Also, I should say we are not training in any way on precipitation. So we do not use the precipitation coming out of our fine resolution model or reanalysis as any part of our training. We're training on temperature, moisture, and wind tendencies because those are the prognostic variables of the model. Precipitation is not part of our loss function. So agreement on precipitation is actually a more impressive achievement than if we actually had trained to get good precipitation.
Yeah, so SJ always like to say that reanalysis is kind of, or precipitation is kind of the poo-poo of a reanalysis scheme anyway. That's where all the mismatch between the model and the input data tends to wind up.
Yeah. I see you have too much sensitivity over the monsoon regions, and that's particularly true of the baseline FV3 GFS model. We actually, our machine learning scheme actually damped some of that out. But yeah, I mean, how well GPCP works over the Himalayas, for instance, that's a really good question, right? But I think it's fair to say that the baseline model precipitation is so far too high that it's not compatible with any observational data set. Okay, I think that's all the questions that I see so far. If there are any more, please put them in the
Chris, can I ask a question?
Yeah.
Yeah, from your experience with this machine learning, the techniques to improve the parameterization, what do you think the areas, the biases in like UFS, like GFS,
you can make a most significant improvement in the model
based on what I'm
biases.
seeing here.
Yeah, you're right.
Okay, well, that's within the U.S. Well, okay, so what we would hope to do now, again, so I'm going to preface this by the fact that here we're working with coarse resolution versions of FV3GFS. So if you want, the target application for them is, not really GFS, but CFS, so say C384 simulations at longer timescales rather than say C768 or even higher resolution that we might be using for operational forecasting. I guess what we would hope to do better is we might be able to better represent the diurnal cycle of convection coming off the Rockies, although I do know that that's improved significantly at 25 kilometers. So a good question whether we can improve that. One thing that's really clear, well, at least with the 200-kilometer version, by these nudging tendencies have an enormous amount of interesting information about your parameterization biases encoded in them. And so just looking at your nudging tendencies is actually very useful. It's sort of like if you use a model in a DA framework, looking at the, the innovations or whatever, analysis increments, and learning from them. But in particular, we learned that the momentum nudging tendencies, say, associated with flow over the Himalayas were huge. And so basically that the model is hugely biased at 100 and 200 kilometers in how it represents orographic drag through its various means, both surface drag and gravity wave drag. And, in terms of retuning parameterizations, you could definitely learn a lot by looking at this. I think even in an operational setting. I don't know if that answers the question.
Yeah, thank you.
I think there's a lot of potential for using this kind of method within the operational version of FV3GFS if it's tightly integrated into the whole DA cycle.
Okay, if there aren't any more questions, we can wrap up. Thank you, Chris, for your presentation. And if anyone has any other questions, you can always email them and we can address them. Thanks, everyone.
Okay, thank you for the invitation.
Sure.
Okay, thank you.
Bye.
Thank you, everyone. Bye-bye.
Okay. Okay, thank you so much, Chris.